Thanks for inviting me here, and it's my great honor to speak here in front of this great crowd. And as usual, this talk is going to be super simple, and I hope everyone can understand and enjoy the talk. There's no concrete math, it's very simple. So the goal of the talk is to understand the hierarchical learning process in multi-layer neural networks. So what is a hierarchical learning in multi-layer neural net? It just goes like this. So during the training process of a deep neural net, let's say on image data set, so your first layer is going to learn features that represents a very basic knowledge of the data. Like, for example, in image, you'll just learn these edges that are straight lines of the image. And then your second layer learns features that composes the first layer in the most basic way, such that you compose these lines to be some simple curves that represent the corners of the data of your image. And then the third layer learns features that composes the second layer feature in a very simple way, like you just put some curve together and you represent those simple compositional objects. And so the main important thing is the complexity of the features as a function of the input. They just grow gradually with the layers goes. So there's no sudden jump in this process. And then there is another very important part is that we are training the higher level feature. It actually improves the quality of the lower level feature. So the concrete evidence is like the layer-wise training process where you just train the first layer and you make it fixed, and then you train the second layer, and then you train the third layer. It typically cannot match the performance of training all the layers simultaneously. So the lower level features are not really very good if you only train them. For example, the quality of the first level feature is not very good if you train the first level feature. It's just when you train all the layers together, the quality of the feature can get improved, and even in the later stage of the training process. Now the question is, how can this happen? I mean, what is the theory for that? How do we reason about this process? And in this talk, we present a formal proof of this hierarchical learning process, and under a model of multi-layer dense net with quadratic activation functions. And so the proof will go like this. So we assume there is a multi-layer target network that decomposes this data hierarchically. That is a dense net with quadratic activation function. You can think of this as the network that you train, like the final network you obtain after training. And then we will show how training a neural net from random initialization can recover this hierarchical decomposition, this multi-layer neural net, and by learning each layer gradually. And also how does the feature get improved by training the higher level features. Okay, so let me describe the target network. It's very simple, so it's just a dense net with quadratic activation, just look like this. So you have an input layer that has it's a linear function of the input, and then you raise it to a quadratic activation. And then your second layer is a linear function of both the input and the first layer. And then you raise it to a quadratic activation, and so on. And then your final layer is a linear function of the input and the linear function of all the previous layers. And then you raise to a quadratic activation. So that's the standard architecture of dense net. We didn't do anything. So the only assumption here is that the layers are getting smaller and smaller as the neurons are getting smaller and smaller as the layer goes higher. And then the final output is a linear combination of the outputs of every layer. So we assume some regularity condition of the network, which just the first one, it just says the singular value of each WLJ are constant, and the WL are -1 and 1. So the networks, there's no very weird shape in this network. And then the more important assumption is that we assume there is an information gap of all the layers. So the output depends on, it's a summation of all the layers, but it's a weighted summation, and the lower level layers are more important. For example, in this picture, the lower level layers, you can think of it as the edges of the image. They are more important than the higher level features. So they contribute more to the final signal. And that's our assumption. And the learner network now is just an over-parameterized dense network with quadratic activation. It has the same structure, just the neurons are larger. And so this is a main theorem. So the theorem says that over a certain input distribution that it can be non-spherical Gaussian or even mixture of non-spherical Gaussian. And for every constant L, you given like linear in the input dimension times the polynomial in the hidden nodes of the target network, mainly training examples, the SGD can recover a ground truth network with generalization error epsilon very efficiently, because the number of neurons in this network is probably in K1. So the total number of parameters is D times this. So it just the time is linear in the number of parameters times the number of samples. So you just need to go, so it's very efficient. And for general layers, it's probably gonna be look like this. And the main message is the target function is a degree 2 to the L polynomial over D dimension input, because the quadratic activation has L layers, so the final degree is 2 to the L. So the other learning algorithms, such as brute force search or matrix sensing or kernel method, would typically require running time either 2 to the D for just brute force search, or sample complexity that is D to the 2 to the L minus 1 if you do it very carefully. But still, they are not very efficient compared to learn it using a neural net. And yeah, our result is like a hierarchical generalization of matrix sensing, which is only for L equals to 1. And actually, to the best of my knowledge, this is only theoretical result of learning a deep neural net via SGD, where the target function is not directly learnable by other algorithms, such as kernel isotonic regression or tensor decomposition. So typically, this is a philosophical reason, because typically if you do theoretical reasoning of how neural net work, it just says they are simulating something that we know, so it works. But if it's actually simulating these algorithms, then why do we use deep learning in practice? And in this work, we will show that the multilayer neural net is doing hierarchical learning that is not really achievable by all the other known algorithms. So let's start with the intuition of how the hierarchical learning goes with a very simple example. Just look at this. The first layer is a quadratic function, and the second layer is a quadratic function on the first layer. And so what is ideal learning is just the first layer learns this quadratic function, then it feeds x1 and x2 squared to the second layer, then the second layer learns a quadratic function, and it solves the problem. But if you think of that way, there is a very big bug in this proof. That is, why the first layer feeds x1 squared, x2 squared? Why can't it fit in this weird basis? I mean, maybe neural net just prefer this basis instead of the standard one. And of course, the summation of these two is also equal to the original quadratic function. But the main issue is the quadratic function of these two. It cannot reconstruct x1 squared force plus x2 force. So if you just learn this instead of the standard basis in the first layer, your learning actually died. You cannot proceed. So here is the goal of over-parameterization, is the rich representation over regularization that I don't know is recorded anywhere. It's just by using over-parameterization plus Gaussian random initialization, it actually enforces all the neurons to, instead of learning some fixed basis, it learns something that looks like a Gaussian mixture of the signal. And of course, if you take the expectation over this Gaussian, it's still the target function, but it's very rich. Yes? Oh, okay. Yeah. Sorry. So the target representation is very rich. Actually, the quadratic function of all these neurons, is enough to construct every force power polynomial, including this target one. And so actually the rich representation, it doesn't matter for the current layer, because no matter you represent it in this one, or you represent in that basis, or you represent in the standard basis, you're outputting the same function. But the point is, it is very meaningful for learning the next level features. So that is how the hierarchical learning is influenced by over-parameterization. And then we consider like the correction stage in hierarchical learning. Let's say instead of having the very basic signal, now my second layer is more fancy. And then maybe the first layer learns a quadratic function that has some error because it's overfitting to the second layer force power things. So it's not going to be very accurate. And then the second layer, it takes this input, and then it tries to fit something that the first layer cannot fit, which is a degree 3 and degree 4 term. And it possibly learns something like this. It's also not very accurate because the first layer is not very accurate. But now the main point is because there is alpha in front of this, so the total accuracy of the second layer is actually alpha squared instead of alpha. And then the first layer now gets recorrect to alpha square accuracy because the second layer already learns the degree 3 and degree 4 thing up to alpha square accuracy. So my first layer, I don't need to overfit to the degree 3, 4 signal anymore, so I get more accurate. And then the second layer, because the first layer has a more accurate input, and the second layer is probably going to be more accurate as well because it takes a better input from the first layer. So now it's accurate up to accuracy alpha squared. So you'll see the role of having this information gap, which is alpha smaller than 1. So you can proceed this process forever. And so here is general picture. You have the input, and the first layer learns some quadratic approximation of the target function. It's not very accurate because it's overfitting to the higher level ones. And then your second layer learns a quadratic function on top of the first one by the rich representation given over-parameterization. And now the second layer is going to correct the first layer because the second layer is there, so the first layer doesn't have to overfit to those features that it cannot learn. And then the second layer gets retrained, and then the third layer starts to learn. And then the third layer is there, so the first layer is going to be more accurate because it doesn't need to overfit to the feature that it cannot learn. That is the role of the third layer. And then keep going, the third layer is going to correct the second layer and just keep going forever, and the third layer starts to learn. So it's the whole training process of the hierarchical learning goes like back and forth in this way. And actually, in this work, we don't really train the neural net in this way. We train all the layers simultaneously. So this back and forth is rather implicit. So, and if you train together, it's going to look like this. And so the summary is, so we studied the process of hierarchical learning. And to the best of knowledge, there's no known algorithm that can actually do this hierarchical learning process because like all these algorithms are relatively one-shot. And so the open direction may be generalized to real-world network or remove the information gap assumption. But actually, in our earlier paper, we show something that this information gap is kind of necessary. So you see when the information gap is smaller than 1, which means the higher level feature has higher weights, then the even deep neural net stops to learn this decomposition, like the yellow and blue lines. So if you want to look at that, you can check our earlier paper. Okay, thanks.
Do you know how to present this? All right, so I'm going to give a very quick overview of my work on the effect of neural net architecture on training performance. There's, of course, been a lot of recent progress on understanding the role of, on the behavior of SGD on neural nets, and in particular on very wide neural nets. But there's still, of course, lots of open questions, and we sort of extend some of this recent work on understanding the effect of overparameterization and the neural net model architecture on optimization performance. And our approach is sort of going to be to identify this condition, which we call the gradient confusion condition, which affects the convergence of SGD. And we show that using this gradient confusion condition, we can establish direct relationships between the network depth, the layer width, input dimension, and training performance. So what is gradient confusion? We consider minimization problems where we're minimizing this function f defined over parameters w, which is where the function is defined as an average of objective functions corresponding to each training sample. And for this set of objective functions, this has a gradient confusion of eta, which is non-negative, if the pairwise inner products between the gradients has a lower bound negative eta. So intuitively, this sort of means that it's some sort of bound on how much the gradients, the stochastic gradients disagree with each other. And it sort of tells you something about how using one stochastic gradient for an SGD update, how much that affects the loss on another training, the loss on another training sample. This, of course, has connections to the gradient variance, which we elaborate on in the paper. And so defining this condition, we sort of analyze, we have two parts in the paper. We first analyze how the gradient confusion condition affects the convergence of SGD. And then we sort of look at how the neural net architecture affects the gradient confusion condition, and this in turn helps us understand how it affects optimization performance. So the first part of the paper is we show that SGD is fast when gradient confusion is low. And so, for example, you can prove for smooth, strongly convex functions that with constant step sizes, SGD converges linearly to some neighborhood of the minimizer. And the size of this neighborhood, the noise floor that it converges to, depends on the gradient confusion term, so which is eta over here. So when gradient confusion is small, you have fast convergence to close to the minimizer. Now, of course, the natural question is, when is the gradient confusion small? It's very easy to prove that for linear overparameterized linear models, random linear models, the gradient confusion will be small. But what about neural nets? So in this talk, I'm just going to give one result that we have in the paper. This is analyzing the effect of the neural net architecture at initialization. So we consider a neural net where the input is x, and it goes through all these layers of operations through standard nonlinearities, and we define the maximum width of any layer as L and the depth of the neural network to be beta. For this case, we assume that we consider like standard weight initialization strategies that are popular in deep learning, as well as a random data model. So all of our inputs are randomly sampled from a d-dimensional sphere. In the paper, we relax these assumptions as well. Under this setup, we can prove a concentration bound, which shows that the gradient confusion bound holds with probability at least this expression. And the key thing to note here is that the probability of the gradient confusion bound holding decreases as the depth increases, and the probability increases as the layer width gets bigger, as the layers get wider. So combining this result with other results we have in the paper, you can show that training gets harder. You can prove that training gets harder as the network gets deeper, and training gets easier and faster as the layers get wider. We do a bunch of experiments in the paper that confirm these theoretical results, as well as additional results on batch normalization and skip connections. The paper that's up on archive is an older version. We'll upload a newer version in a couple of days. Thank you.
Hello everyone, my name is Mahyar Fazlyab from University of Pennsylvania. Today I'm going to talk about a semi-definite programming framework that we have recently developed for sharp estimation of Lipschitz constant for deep neural networks. And this is a joint work with my colleagues at UPenn. So given a function represented by a feed-forward neural network, our goal is to find the smallest constant L2 such that the Lipschitz continuity property holds globally for all x and y. So why do we care? First of all, the Lipschitz constant can be used as a global measure of robustness or sensitivity of the neural network. Explicitly, if we have access to Lipschitz tight estimation of the Lipschitz constant, we can use this quantity to find the radius of maximum perturbations on input samples for which there is no adversarial examples. There are other utilities to estimation of Lipschitz constant, namely closed loop stability analysis of neural network controllers, training robust classifiers, deriving generalization bounds, and other applications. And our framework provides a useful and novel tool for all these applications. So what makes this problem difficult? The presence of activation functions. So in order to combat this difficulty, we use a framework which is from robust control, namely incremental quadratic constraint. So explicitly, given a function, nonlinear function phi from Rn to Rn, incremental quadratic constraint is defined by a set of symmetric and indefinite matrices for which this quadratic inequality holds globally for all x and y. And by definition, this set of matrices is a convex cone. So this is the first step towards simplifying the problem of estimating the Lipschitz constant. So why is this framework important? The main idea is as follows. So instead of analyzing the original neural network with Lipschitz constant L2, the problem is NP-hard, we build a simpler network instead, where we remove the activation functions and replace them with the quadratic constraints that they satisfy. In this way, we construct a family of quadratically constrained linear networks. There's no activation functions anymore, and analyze the Lipschitz property of this with this linear network instead. Our key observation is that the Lipschitz constant of this simpler network is a guaranteed upper bound on the Lipschitz constant of the original neural network. Since we have a parameterized family of linear networks parameterized by the matrix Q that characterizes the incremental quadratic constraint, we can optimize over this family and find the best upper bound on the Lipschitz constant of the original network. So our main result is as follows. We can find the best upper bound on the Lipschitz constant of the true neural network by solving the optimization problem in one, and we can pose this problem as a semi-definite programming problem. And this result will appear in NeurIPS 2019 as a spotlight talk. I'm not going over the details of derivation, but just a little bit of how we construct this framework. So how do we construct the incremental quadratic constraints for activation functions? We use the slope restriction property of activation functions. All commonly used activation functions in neural networks satisfies this slope restriction condition characterized by these two constants, alpha and beta. Using this local property of activation functions, we can build incremental quadratic constraints for concatenation of the activation functions throughout the entire network. And this family of matrices is given by this lemma that we have provided here. And this is just a visual proof of how we do that. A concatenation of neurons across one layer. Take two arbitrary neurons. Write the slope restriction condition between these two neurons. And then we can convert this to a quadratic inequality, and a conic combination of all these quadratic inequalities for all possible combinations of neurons gives us the result that we want, a family of incremental quadratic constraints that characterize the activation functions. And this is the main result formally for one-layer neural networks, and we have the result for multi-layer in the paper. So consider that we have this neural network, one-layer neural network characterized by the weight matrices W0 and W1 and biases B0 and B1. And we assume that the activation functions are slope restricted in the interval alpha and beta. And we define the following matrix inequality, parameterized by constant rho, and the matrix T that parameterizes the quadratic constraint. And the main result is that if this matrix inequality is satisfied for some matrix T and some constant rho, then the square root of rho is a guaranteed upper bound on the Lipschitz constant. And this leads us to our main result, which we can minimize this rho subject to this matrix inequality. And as you can see, everything is linear. So we have a linear objective subject to linear matrix inequality constraints. So this is a convex optimization problem and can be solved in polynomial time. So we did experiments on MNIST data set. Explicitly, we trained 3 neural networks using 3 training methods in order to study the effect of the training on the Lipschitz constant. So we used the Adam optimizer, the LP train of Wang and Coulter, and the PGD train of Alexander Madry. So we trained the neural networks on the MNIST data set, and we found the we computed the histogram of the perturbation balls, epsilon perturbation balls on the input of the neural networks. And these histograms tell us that as these histograms are shifted to the right, this means that the neural network is more robust. And this has a direct correlation with the Lipschitz constant of the neural network. So neural networks that have lower Lipschitz constant tend to be more robust. And on the figure on the left, we compared our results with other numerical solutions in the literature, and to the best of our knowledge, we have the tightest bound in the literature. And that's the details of experiments which I described, and thank you so much.
Okay, so hi everyone, I'm Maithra, and I wanted to talk about understanding transfer learning with applications to medical imaging. This is based off of our paper, Transfusion, Understanding Transfer Learning for Medical Imaging, with 3 of my fantastic collaborators, Qiwan Zhang, John Kleinberg, and Sami Benjo. So with all of the successes we've seen in deep neural networks in computer vision, problems in natural language, robotics, as well as newly emerging and rapidly evolving areas like medicine and healthcare, transfer learning has really emerged as a central technique. In transfer learning, we start off with a randomly initialized neural network that we first train on a task, task A, and this is known as pre-training. This network then converges to a set of weights, the pre-trained weights, and then we continue training this network on a new task, task B, and this is known as fine-tuning. This gives us our final model, and what we really care about is the performance of this final model on task B. Why train on task A at all? Well, the belief is that if task A is diverse and general and complex enough, we'll learn features on task A that can be reused to help performance on task B. So this simple paradigm has been extremely successful, especially in computer vision, where it's now standard to pre-train convolutional neural networks on large data sets of natural images, with ImageNet being the most popular example. And then most recently, as we saw in an earlier talk, transfer learning has also become very popular in problems in natural language processing, particularly thanks to a very influential paper called BERT. In this rapidly evolving area of deep learning for medical imaging, transfer learning is also becoming a de facto standard. So here, the setup is that you download a standard pre-trained ImageNet model and then fine-tune it on different medical tasks of interest. And these can really be diverse, from ophthalmology to early prediction of Alzheimer's. Now, if we pause here for a moment, this setup is actually quite surprising. The underlying principle behind transfer learning is that this pre-training process is going to provide us features that are going to be useful for our target task of interest. But the data in ImageNet, things like dogs and fire trucks, is really pretty different to our target task of medical imaging. So it's a bit of a mystery as to how and why this works. And this underscores this more general research into transfer learning, which is that despite the fact that it is so popular, we're only now beginning to understand how exactly it's working. And to point to one example of this, a very interesting recent paper asks this question: do better ImageNet models actually transfer better? And the answer turns out not to be straightforward at all. There's a very nuanced relationship depending on the kinds of regularization you use, the data set, the target task, the size, that lead into this great diversity of results. So this was in the natural image setting. And in medical imaging, which is this very exciting area, there are many, many open questions. And this was really the focus of our study. So we started off, as you sort of have to, by performing a performance evaluation of transfer learning. And so what we did is we took a couple of different medical imaging tasks and several different neural network models. We looked at standard ImageNet architectures, and we also looked at a family of much smaller, lightweight, simple convolutional networks that we called CBRs. And we evaluated how transfer learning did in all of these settings. And our takeaways were actually pretty surprising. Firstly, transfer and random initialization actually perform comparably in most settings. Secondly, these small, lightweight CBR models performed about as well as these standard ImageNet architectures on these medical tasks. So relatedly, what we saw is that ImageNet performance isn't really indicative of how you're going to do on these medical imaging datasets. So given that performance is so similar, does this mean that transfer learning is having no effect at all? Or in particular, is the fact that we're actually pre-training affecting the representations of these neural networks, or are they all converging to the same kinds of things? To answer this question, what we really want to do is take networks trained from random initialization and take networks trained from pre-trained weights and try and understand whether their latent representations are similar or different to each other. This is difficult to do naively because there's no natural alignment between neurons in one network to neurons in another network. But we can draw on some prior work and tools we've developed to do this, SVCCA, that overcomes this alignment issue. So we can go ahead and train a population of neural networks from random initialization, a population using pre-trained weights, and then compare the representations across these two populations. As a baseline, we also do a comparison of representations within one population. What do the results look like? Well, here along the x-axis are two different architectures we tested this out on, and on the y-axis is a scaling of how similar these representations are. So what we see is that representations between pre-trained networks and networks from random initialization are clearly smaller than the similarity of representations all trained from random initialization. So in summary, pre-trained weights are affecting the hidden representations. However, there was also an interesting confounding effect we noticed, which is that larger models were changing less than smaller models. In particular, for large models, there was a surprising correlation between the similarity of representations at initialization to the similarity of the representations having trained on this medical task. This wasn't true for the smaller models that were changing much more through training. Finally, we looked at the effects of transfer learning on convergence speed. Transfer learning significantly helps speed up convergence. But what was very surprising is that many of these effects can be recovered just through scaling. So if we initialize just like random initialization, but scale according to the pre-trained weights, we actually see significant gains in convergence speed. Thank you very much, and please come check out the poster.
Hello everyone, my name is Valentin. Does that work? Yeah? Okay. Okay, so I'm going to present you some work about information matrices and generalization. So this is joint work with Nicolas Leroux at Google Brain Montreal, my supervisor Yusha Benjo, and some other Googlers, Fabian, Bart, and Pierre-Antoine. So first I'm going to tell you what are the information matrices. There are three of them, and probably you know like at least two. There are the Hessian, the Fisher, and the covariance of the gradients. So the Hessian and the Fisher are curvature matrices, meaning that they can be used to approximate a function to a second order. The Hessian with like a Euclidean ball approximation constraint, and the Fisher with the KL constraint. So these two matrices can be used in optimization. They lead to algorithms like Newton method or natural gradient. The other matrix I'm going to talk about is the covariance matrix of the gradient. So when I say covariance here, I mean the uncentered covariance. I'm going to show you the equation. It's like expectation of gradient transpose. It's when you have a stochastic gradient problem, it's basically the structure of the noise encoded in your gradients. So here's what they look like. So as you can see, the Hessian and the covariance, the first two metrics, H and C, are taken with expectation with respect to the actual data distribution. And when I mean data distribution here, I'm speaking about the true underlying data distribution. The Fisher, on the other hand, is taken with the model distribution. So you can see here that the Fisher has two expressions. One that looks a lot like the covariance, and one that looks a lot like the Hessian. So why is this important? Well, it's important because of that. When your model actually recovers the data distribution, all these matrices are equal. And many people have been actually using this thing to say that all the matrices approximate each other. This is not necessarily true. This is only true at the exact optimum if you're even able to reach it. Like some models called misspecified models can't even achieve that. So we're going to study what is the link between these matrices and why does it matter for generalization. So here, this is an empirical study on neural networks. So we trained many neural networks on CIFAR10 with different architectures and hyperparameters, and we looked at two quantities. One is the ratio of the traces. So we look at is one matrix much bigger than the other, and the other quantity looked at is the cosine similarity. So if these two quantities are equal, it means the matrices are equal. As you can see here on the first plot, the Hessian and the Fisher in green have the same scale, basically. However, the covariance, C, is much bigger than both of these matrices. On the second plot, you can see that the Fisher and the covariance are always extremely well aligned, and very fast in the training, the Hessian becomes aligned with everything. So what happens is that all these matrices kind of point in the same direction in space. It's a very high dimensional space, so these similarities are really high, but the covariance is much bigger than these two matrices. So they're not equal. The Fisher does approximate well the Hessian, even for neural networks, but the covariance is somewhat different. So why is this important? Why does it matter at all? So it does matter for like optimization. If you replace the Fisher with C, which is often called the empirical Fisher, it can lead to many issues in your algorithm. But we're going to have another look at that and look at why it matters for like generalization. So indeed, there have been many works that I've been noticing that neural networks have far more parameters than number of data points, kind of implicitly saying that the neural network, it's weird that neural networks generalize because they have a very high capacity compared to the model, meaning that implicitly this means that the number of parameters looks to be like a sensible measure of the capacity of the model. But that's a fallacy because it's only true in some cases. In most cases, the number of parameters is not necessarily a good measure of capacity of the model. And when I say that, I mean that the number of parameters can actually be used to estimate the generation gap you have, but this is only true if the Hessian is equal to the covariance. So actually, we derived this equation and realized that it already existed. This is called the Takeuchi information criterion. It was published, I think, in Japanese in the 70s, and it has only a few hundred citations. But the thing is, you can build an estimator of the generation gap. So I say estimator, it's not a bound, it's an estimator that uses the Hessian and the covariance. So you can see here that this estimator is 1 over the number of samples you have times the trace of the inverse Hessian times the covariance. So this thing here is an estimate of the gap your model can have around the optimum. And in the case where your Hessian is equal to your covariance, you find trace of identity, which is the number of parameters of your model. But as we said, as H is not equal to C, these two things are not going to be equal. And this thing, you may have heard of that, is called the Hierarchical information criterion. And so here we study for machine learning models, how does this criterion work? Do they actually estimate the gap? So you can see in red the number of parameters, AIC. So in the first experiment, we have a 2-layer neural network trained on CIFAR10, and we vary the hidden layer size. So you can see that as we vary the hidden layer size, of course, the number of parameters rise. But the gap here in blue, you can see that it has some kind of a peak behavior. Like for small models in underfits, it becomes to the under overfitting regime, and the gap slows down. And the Takeuchi information criterion that uses the Hessian and the covariance captures this behavior. And now if we look at another experiment, the one where we shuffle the label corruption ratio, meaning that we take some images and we shuffle the labels and we train on that, you can see here that the number of parameters stays constant, of course. But the gap is going to increase if you have more randomized labels. And when we use this TIC, here we see that it also captures this behavior because the Hessian and the covariance depend on the actual data, not only on the parameters of the model. And so we also have another experiment here, so a larger scale where we have many neural networks trained on many different data sets, and we looked at does the Takeuchi information criterion actually capture the generation gap? And we see that we do actually have a pretty nice correlation that the flatness is not really able to capture. And also flatness is a quantity that is not invariant under reparametrization, that doesn't work for linear models, while the Takeuchi works for linear models, is invariant under reparametrization, and has some nice properties. Of course, this quantity, TIC, is really hard to compute. Yes, I'm going to finish in 1 second. So we clarified the link between all these three matrices. We don't really advocate for the use of the Takeuchi information criterion, as some reviewers believed. It's really impractical. I would never recommend to use it. Use cross validation, but it does give some good insights on what curvature noise can mean and the relationship to generalization. Thank you, everyone.